Hello, class. Today we're going to discuss a little bit about a new topic. We're going to talk about something called trees. Not to be confused with the little planty trees you plant in the ground. Ta-da. That's a hideous tree, I know, but cut me some slack. Anyway, the trees we're going to be discussing are actually going to be a little bit different. Now, uh, a tree is a data structure that we can store information in. We can gather it, we can put it in, put it out. There are a couple of different types of trees. There's binary search trees, which we'll discuss. There's a couple others, red, black. Uh, Trees are typically used for a couple of different reasons. One, they're actually very easy to deal with sorting numbers and retrieving some information. Two, think of decision trees. If you ever thought about branching dialogue in a game or something like that, you have, a choice to make between one choice and another one, right? Well, depending on what choice you make, you know, you may go one direction or you may go another. So if I make this choice, maybe I go there. If I make this choice, maybe I go there. Maybe I have two or three choices in a decision. Something more like this. Let's just go ahead and remove the other, make it a little more logical. Maybe I have three choices. I can choose to kill this person. I can choose to spare them. I can choose to do something else. And each one of these choices gives me a branch, basically, I can use to go to another, dialogue option or another story option or something along the lines of that. This leads me to another choice that I may not have had before. And this leads me to another choice. And this leads me to another. And then maybe I have two or three decisions on those. This is your typical regular tree structure. Uh, it, each one of these little items here would be called a node. We've dealt with nodes before. Our linked list had nodes. Uh, Other structures we typically use have nodes too. Now, this is of course just a very basic tree. It can have as many branches as it wants. Not super structured, but you would kind of use this like for a decision tree. Or maybe AI. You ever think of this? Let's say this node represents what the board looks like, at the start of the game. The computer has to decide what move to make. How does it decide what move to make? Well, let's say you go first. Well, it's going to have a list of what the board would look like, if you make this move. So it will cut pretty much all the decisions that don't involve that. It'll check the decisions as far as what move to make next by looking at the next branch of the tree. Now every piece is worth, a certain amount of points. Rook, pawn, worth pitiful amount of points. Now if it only looks one move ahead, it can see what move you make, maybe what move it makes, let's say. Let's say you can see a couple of different moves and how all these things play out. So it goes one branch ahead. Boop, 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 boop. You make a move. Well, it has to find an appropriate, all right, this is that branch. Here are the moves I can make. Which one's the most beneficial? Which one gets me the most points? Now, if it is incredibly, a well-programmed AI, it would probably start thinking, several moves ahead instead of just, one, two moves ahead. This means that it can look probably, three or four moves down the branch. And what it would do is calculate. All right, if I go down this branch, how many points do I have? How many points does the other person have? Points being how much each piece is worth. How many did I kill? How many did they kill? And it's going to look down this tree and see which one's worth the most points. Now, whichever one's worth the most, that's the move it'll make, typically. Now, if it's only thinking one move ahead, maybe it moves one move here, and that's the best move in this one turn. But that totally screws it later on. Like, you know, it gained 2 points here, but lost 10 in the next run. Uh, maybe it was far better to take one of these other branches, even though, maybe they lost 3 points here. But then they took 10 or 15 points in the next couple of moves after that. So it all depends on how that AI works. And of course, you have AI in like war games and stuff like that. That's a little bit different because it's not really making decisions, but you kind of get the idea. Programming a chess or checkers decision board would be kind of not so dissimilar from this. Now this is just your basic tree. Now there is another thing called a binary search tree. And it's very structured. It has a main node, your root is what it's called. And then it has a left and a right child, and they call them children. This would be the parent. So I would have a left, I would have a right. Each one of these nodes would have a left and a right, potentially. Left, right. So, whoa. So as you can see, it's very, very structured. Uh, Now, it's not always going to have left and right. Maybe this one doesn't have any. Maybe this one just has one on the side over here. And just to make it a little easier to see, I'll make a couple of lines here. But this is typically what your binary search tree looks like. Now, a binary search tree is a little bit different in that its structure goes a little bit like this. Whatever number I insert goes at the top. Let's say, 8, for example, goes there, right? And maybe I want to zoom in a little bit here. But and then, I decide I want to insert another number. Let's say 4. The way a binary search tree works is if it's smaller, it goes to the left. If it's larger, it goes to the right. So if I insert a 4, it's going to go left. And if there's nothing there, well, it'll go there. If I insert a 10, 10's bigger than this, it goes to the right. 10, like so. Now let's say I insert a 2. Well, that's less than this. There's something here, so it's less than this. That means I go left. There would be nothing here. I would insert my 2. Now, what if I inserted a 5? Well, 5 is less than this, so we go left. But 5 is greater than this one, right? So that means I go right. 5. What if I wanted to insert 20? Bigger than this, go right. Bigger than that, go right. And there's nothing there. So my 20 would end up being here. And if it was, let's say 9, 9 is bigger, 9 is smaller, I would go here. And of course 1 less than 1. You kind of see how that works out. Now of course I already outlined the nodes, but you kind of get the idea. If I wanted to insert something different, let's say a 40, well, it's bigger, it's bigger, it's bigger. The 40 would go to the right of this. Now currently there's nothing there, so I would create a node and plug it to the right. This is how a binary search tree works. Now, there are balanced and unbalanced trees. Typically, it should be fairly well balanced, but if I did, let's say, 8, 7, 6, 5, 4, 3, 2, 1, it would just make one long chain down this way. Or 1, 2, 3, 4, 5, 6, 7, 8, it would make one chain down this way. So you kind of see how that would work. Hopefully. Now, of course, there are algorithms to rebalance the tree. Basically, you take everything out, get the middle, pop it in, and then insert the nodes, and they'll go however they're supposed to go at that point. But for now, this is kind of how a binary search tree works. We go to the left if it's smaller. We go to the right if it's bigger. There are a couple of traversals we'll discuss. There is in order, post order, and pre-order. Traversals is what they're called. So we'll cover these three here in another video. So you'll kind of know how those traversals work. And what a traversal is basically I go through this tree and print things from it. But I do it in a certain order. So just to give you a hint, in order, if you want to know what that sounds like, it's just going to print in order that I go through the nodes. Pre-order, and actually it's a recursive algorithm. It's actually like 3 lines of code. You'll be pretty surprised when you actually see how it works, because we're going to have to cover the code of how that works as well. But we'll cover that a little more fully in another video when we start putting it together. But this is your basic idea of trees. Hopefully that made some sense. Again, it covers everything from decisions, AI, uh, basic game structure, but it can also store information, like a binary search tree, for example, uh, and make it easy to access. To access a number, well, if I was searching through an array, what would I have to do? Go through the entire array until I found it, even if it was in order. If it was in order, I'd at least know when to stop. If it wasn't, I'd have to go to the end, possibly till I found it. This, however, if I'm looking for, let's say, number 3, well, I know it's got to be on the left side, so that cuts half of this tree off. I know it's got to be on the left side of that. That cuts half of that off. 2. Oh, dang. That means it needs to be at the right. There's nothing there. Tree 3 isn't in the tree. If I'm looking for 5, I know it's less than this. I know it's greater than that. Up, found it. It's much easier to find it because every time I go down a node, basically I'm cutting the tree in half. So searching for stuff is significantly faster with trees. Uh, as is, inserting. I just left, right, plug it in. But again, we'll see that here a little bit later. If you have any questions or anything, just ask, leave some comments, uh, or send me a message.